Okay, hello everyone, good evening. Um,
Good
so,
evening.
yes, so I was told decision functions of knife base has not been done from that part. So, we'll start from there and then we will do some problems. Okay, this is okay. So, we have to look at decision functions of knife base. Right? PDF will not be shared in the calendar, the PDF will be shared on the portal. So you want here you want something which can help us decide that if let's say this is my data set and let's say this is my another uh, like another label maybe, then what is the decision boundary is that will separate my positives from the negative. I will separate one of my class to another class, right? So we have to figure out how does the decision function looks like. Okay. So see, like we know that if let's say if we have two classes, so if let's say the classes are R0 and 1, okay. So what do we say? Like we'll predict my y test to be equal to 1 if probability of y test given some x test, y test is equal to 1 given some x test is greater than probability of y test is equal to 0 given x test. That's correct. So this is how we will predict. I mean, this is how we will predict the label for my y test given you have an x test given to you. Now, or let's say if you have more than 2 labels, 3 labels, right? So basically, you want to check what is the probability of y test to be of one label given x test, and the different values of y. I mean, the different labels you have, you will calculate all of these probabilities, and then based on which probability is the highest, I would say my x test would predict the y to be that y. Okay? This is how we'll check. Now, for simplicity, let's assume that we only have two labels, which is 0 and 1. Now I want to test, uh, like if I have to predict y test to be 1, then this should hold, right? This condition should hold. But now from Bayes' theorem, what do we know? We know that uh, probability of y test equal 1 given x test, we can write this as x test given y test is equal to 1 times probability of y test is equal to 1, right? Divided by probability of x test. And if this is greater than, this should be greater than, I mean, same thing. So you are going to get probability of x test given y test is equal to 0 now. Y test is equal to 0 times probability of y test is equal to 0 divided by probability of x test. Now we see that on both the sides, we have the denominator to be same, right? So we can, and these are probabilities. We'll just assume the probabilities are non-zero. So what will happen now? I mean, we can ignore the term in the denominator because this can go on the other side, this can go on the other side, it just gets cancelled out. So what we will have is this numerator should be greater than the right hand side of the numerator, right? So if you have to write it, we can say probability of X test given Y test is equal to 1 times probability of Y test is equal to 1 divided by probability of X test given Y test is equal to 0 times probability of Y test is equal to 0. And this should be greater than 1. Okay. So this is what happens. Now we know what these probabilities are, right? We know, so what is probability of X test given Y test is equal to 1? So what is this going to be? Anyone? You want to guess?
It is a likelihood.
Hmm? Yeah. So what is it going to be?
Product over like I is equal to 1 to t.
Yeah. So product over
I equals 1 to d.
1 to d, assuming there are d features. So probability
Probability
of any feature, and since it is Y test takes the value 1, I would in the superscript I will write as 1. And since it is the estimate, so we can use the hat. Okay, and this to the power of fi. Basically, our Bernoulli distribution is what we have, right? So just to give the context here, let me write. So what we had assumed is the very first thing, that probability of y is equal to 1 is p. Right? If value y is equal to 1 is p. Then probability of x, which is nothing but a d feature vector. So we have f1, f2, so on till ft. So we have d features given the y. And what is this probability going to be? This follows basically a Bernoulli distribution. So, and we had assumed this class conditional independence. So this was nothing but if I have to write the likelihood, it is probability. So pi to the power, and for just to denote which class, we have used the superscript. So piy, so p to the power x. So in this case, it is fi, and 1 minus p, which is piy to the power 1 minus fi. Okay. So, and of course, the product is going to be here. So I is varying from 1 to d. So this is a probability that we have for probability of probability x given y. So now, if the estimate is p hat I, then we can write this to be product of pi hat y test to the power fi 1 minus pi hat y test 1 minus fi, where I is varying from 1 to d. Right? So the same thing will hold on the other side. It just instead of okay, sorry. So since we have taken y test to be 1, I can just simply write 1 here. Not required this one. So 1. And this will also be similar. The denominator is also going to be similar, right? So it is going to be p hat I of 0 to the power of I 1 minus p hat I of 0 to the power 1 minus fi, where I is varying from 1 to d. And we are saying this has to be greater than 1. Okay. So to simplify things, we can introduce the log here. So when we introduce the log, this product becomes the summation. Okay. And if I use the log on the right hand side, it's just going to give us 0. So let's use the
Um,
log. Yes.
Ma'am, it could be reciprocal, no? I mean,
Meaning,
If we, when we predict for one, it is greater than one.
mm, for one it is.
I mean, if we predict y test to be one, then it is greater than one. No?
Yeah, then it is greater than one, right?
Yeah, if we predict for zero, it will be, I think, reciprocal. No?
Yes,
You are saying should be greater than one.
it should be greater than one only, no?
Can you scroll up a bit?
So
Okay.
we're saying
If,
predict y test to be one if this probability is greater than y test is equal to zero.
okay.
Yeah, this is fine, no? This is one.
Yeah, okay.
Yeah, okay. So now we can take the log on both sides, and if we take log, this product will become summation, right? And but what we are going to do is like before that, we can just combine these two things. So just look at the first part of these and the second part of these. So the power is same for both of these entries. So it's more like the product of, I can write product of I varying from 1 to d, pi hat of 1 divided by pi hat of 0 to the power of fi we can do. And for the other side, we can write 1 minus pi hat of 1 divided by 1 minus pi hat of 0 to the power 1 minus fi, right? And this has to be greater than 1. Now, if we take the log, my product will get converted to summation, and I can write this to be sum over I varying from 1 to d fi log pi hat of 1 divided by pi hat of 0 plus 1 minus fi log 1 minus pi hat of 1 divided by 1 minus pi hat of 0. Okay? And this has to be then equal to 0. Okay. So, okay. I think we missed. Okay, okay. So we didn't mention what my p y test is. About if y test is equal to 1. So that is p hat, right? That is p hat. And then y test is equal to 0 is going to be 1 minus p hat. So along with this, along with these terms, we also have this sum over log of p hat by 1 minus p hat, right? And this whole thing has to be greater than 0. Now we can just simplify this a little, and let's see. So if we simplify, uh, what do we get here? Huh. So okay. Um. Yeah. All right. So we can keep fi's to be at the same place. So we have fi, and then we can have log of this pi hat 1 divided by pi hat of 0, minus of log of this term, plus I will have log of this thing plus log of this thing. Okay? And I is varying from 1 to d. This is what we have. And this has to be greater than equal to 0. Okay. Now we can simplify this a little. If you have gone to the lecture, you would have, I hope you would have derived it. So Once you simplify it a little, you will see that it at the end it turns out to be of the form W transpose X plus B to be greater than equal to 0. It comes to be of this form. So from here, we can say that like just with the difference that what W is, what B is, that those terms are different. My weight terms are different. Bias term turns out to be different. But at the end, this is the actual expression that we have. I mean, we get the decision function or my decision boundary of to be linear, right? So from here we can conclude that my decision function is, I mean, my decision boundary is a linear for knife base. So I've skipped the proof in between, like it's not, I mean, not a proof. Basically, you just have to work out the math, and we can reach to this form. So if any of you, if you went through the lectures and you found it difficult to understand, you can let me know. I can do it. But if you have not tried, you can try it out. You can write out the proof. Is there anyone who found this to be difficult? This part, doing this part? No. Okay. All right. So I can move. I can move forward. So from here,
So, ma'am,
yeah. Tell me.
so like there is Fi into this log thing, no? Log difference of these logs. So this difference of these logs gives the weight values. No?
Difference of these logs. I have to do the proof. I mean,
We are getting the W transpose X, and X is having the feature values. No?
uh-huh.
So Fi is the features of X.
Correct.
So this inside the bracket there is a difference of log things. No? So
Yeah, yeah. I
those
mean,
should be weight values. No.
yeah, yeah. So yeah, correct. So if you solve for this, you will get the weight. This is your xi, and this whatever it's here, it's going to be a bias term.
Like
So
each weight component.
yeah, you can solve it a little, and you'll get a little simpler form. But this is what my bias is. I mean, I can call this as a bias term, and this is what we get the weights to be. Okay. But it will come out to be of this expression. I mean, you can see from here that it is of the form W transpose X plus P greater than equal to 0. So all we can conclude from here is that the decision function of knife base is linear. Knife base is linear. Okay. So this was about the decision function. Now moving to we have seen where the labels were just 0 1, right? Sorry, the features were binary. Like features, like if we have my x to b, x1, x2, so on till xt, where all of these xi's, all of these features just takes the binary value. Then we saw how to solve such kind of problem. But now imagine that you have these xi's which can take any value. So they all can take any value in R, right? So if your x's can take the value in R, then how can we like come up with this knife base? Like how do we work with this knife base model, right? So this is what we will see now. Okay. So when we are
Ma'am,
saying, huh,
we are getting W transpose X plus B greater than equal to 0. No? Like
yes,
if we predict y test to be equal to 1, so should
correct.
we get like less than or equal to 0 if we predict for y test is equal to 0?
Sorry, your voice is not clear. Repeat again. Should we get?
Like should we get less than or equal to 0 if we predict for y test is equal to 0?
Yeah, yeah. So if you are predicting, like, see, this we got, uh, like we predicted y test to be 1, right? So when we predicted y test to be 1, we got, I mean, this has to be greater than 0. It is this side. So anything on this side, I'll predict it to be 1, and anything on the other side, we'll predict it to be 0. So for the other way, I mean, for predicting it to be y test to be 0, it should be y transpose x plus b has to be less than 0, right? All right. So now we will see Gaussian naive Bayes. Okay, so we saw what the naive Bayes classifier is. Now we will see what is Gaussian naive Bayes. So as this model says, Gaussian naive Bayes, right? And we know Gaussian means
Uh,
uh,
Ma'am,
mm,
sorry to interrupt. That just in the little ahead, before time, you showed na W transpose X my plus B, right?
mhm.
So yeah, here this is what is giving the regression. This is the regression equation. In any situation, whether this anywhere we will be using X transpose W. When we are finding the error, that time also we are using W transpose X minus.
This, you can't say this is regression. I'm saying this is a linear function. This is an equation of a
Yeah,
linear. It's a line, right?
linear regression equation, right? Or,
No, this is the line, no?
okay. But is it
Regression.
not that linear regression equation W transpose X plus B?
No, no. So, see, in linear regression, what is, see, you first of all, you have a data set, which is xi, yi, I varying from 1 to n. Your xi's, now, since the regression, your yi can take any value in R, okay? And there, uh, like, let's say, since we're talking about the regression, I mean, linear regression, so it means I'm going to look at the linear subspaces, right? And we had assumed, like in general, this is the set of all, this is a set of linear lines, right? This is a set of lines. So W transpose X um, is a set of lines. So we said, let's say my H linear is this. Now, assuming that this is a set of subspaces where we are going to look for the function, now we want to see like which, like this is just in general some W, right? We don't know what this W is, we only know our axis. So if we have, I mean, if we have to look in a set of linear functions, then in general this is the this is a set of all the linear functions. Okay. So what is that W that will solve our problem? That was the question. And what was the problem we were trying to solve there? We wanted to solve this problem, like any y that we have and what we have predicted, which is we should satisfy this W transpose X square, right? Varying from 1 to n. So we wanted to minimize this mean square error, right? And
Yeah,
what
yeah.
of W solve that is the weight that we got. But here it's a classification problem. And here we are looking at the linear, I mean, what we got, what all that we got is um, the classifier that this naive Bayes classifier, the decision function that we are getting is also linear. That's all we can say. Regression.
Okay, ma'am, the reason why I'm asking this, sorry if I missed anything earlier also. So in the SSC error or in the Rees loss or LESO is, we are using X transpose W minus Y.
Mhm. Correct.
So the doubt what I'm having is that here to get the value, we are using W transpose X minus YI, but there we are using X transpose W minus Y.
X transpose W minus.
Both will give same value, I think.
What did you say?
W transpose X and X transpose W will give same value.
See, you are again confusing it with mixing it with a matrix and a vector. So when we wrote, like if we go back to the linear regression problem, when we wrote we want to minimize this, this was same. It was equivalent of saying that we want to minimize my X transpose W minus Y norm square, right? And here X is a matrix. It's a D cross N matrix. W is a matrix. It's a D cross 1 matrix. And Y is a N cross 1 matrix.
Okay, and in this equation, x is a vector, is it?
X is a vector, no?
Okay, okay, okay,
Yeah.
okay, fine. We can continue.
Okay. So now if we have to talk about the Gaussian knife base, uh, like we are not now restricting the features to take only linear values, or sorry, only binary values. So we are not saying that my x's are only binary, that is 0 or 1. So now in cases where your x's can take any real value, then how can we modify this knife base as? So the problem setup is again the same. So you toss a coin, and let's say that probability is p, and then again if it turns out to be, I mean, for y is equal to 1, for y is equal to 0, when you have two classes 0 and 1. So we are going to um, like in the space where your the coin lands on head, there will toss, like you can think of it as you can toss a coin, um, not toss a coin. I mean, the data set will actually form a contour. Like it's a normal distribution that we're talking about, right? And if it's a normal distribution, and for different variances that we take, okay, we are going to get uh, like different contours, right? So it looks something like this. So the mean, like when your y is equal to 1, let's say the mean is the mean is mu1, and when y is equal to 0, the mean is mu2. So basically, given y is equal to 1, the distribution of x, we assume that it follows a normal distribution. So distribution of x given y is equal to 1, it follows a normal distribution with mean mu1 and some covariance matrix. Okay, call it sigma. And similarly, on the other side, when y is equal to 0, what we are assuming is given y is equal to 0, the distribution of x is again normal with mean mu2 now, and we are assuming the same covariances matrix, which is sigma. Um, okay, so
Ma'am,
what? Yes, tell me.
why did we opt for a normal distribution over binary from Bernoulli?
What? How did we?
Like we are taking the X test to be Bernoulli samples, no? Each feature has a Bernoulli. Now we are
So
taking as
was
normal.
that on the Bernoulli, like, see there, how did the x look like? Let's say if sorry, if my x is f1, f2, so on till fd. Okay, and these f can take the values only 0 and 1. So for example, let's just do a small example. So let's say x is 0, 0, 1. So I know this is my f1, I know this is my f2, I know this is my f3. What does the naive Bayes says? It says that it has a class conditional independence, meaning given, I mean, probability x given y, I can type this as probability f1 given y times probability f2 given y times probability f3 given y. Right? We could have written this. But now, see, these FIs are taking only two values, either 0 or 1. Each of these FIs, if you see, it takes only two values, 0 and 1. And we know what does this distribution look like. It is nothing but a Bernoulli distribution. Right? And that's how we had used the Bernoulli PMF. Right? So we had written a product of, so p to the power, so let's say for the feature f1, the probability is, let's say, p1. For again, depending on what the y is, to the power f1, right? This is what we will write, times 1 minus p1, in general, if I have to write fi, right? So 1 minus pi to the power 1 minus fi. This is what we have done. Okay. But now what is happening here? Here I am saying these FIs now belong to R. Okay. And if my if the date if some variable, if you can take any value in R, then I can use, I mean, since we're talking about the Gaussian naive Bayes, it means we are assuming that my features follow some normal distribution. They're coming from some normal distribution with some mean and some variance. Okay. So that is why now when we have to write like probability of x given y, uh, like given any y, it no longer follows a Bernoulli distribution. Now it follows a Gaussian distribution. It follows some Gaussian distribution with some mean and with some variance. Okay, and that is why what we have done over here. So given x y is equal to 1, we are assuming that the distribution of x is a normal with mean mu1 and covariance matrix sigma, and given y is equal to 0, let the distribution of x be normal with mean mu2 and variance sigma. So we are assuming the variances to be similar in this case, and a different mean is what we are assuming. So we'll see both cases, like what happens when we assume the same sigma, what happens when we assume the different sigmas. Okay, so that's the only difference I would say basically it has. But now, see, like just like the naive Bayes, which we did for Bernoulli, like binary features, there we had to estimate the p. We had to estimate all these pi hats. But now here there are more features, or there are more parameters that we have to estimate. One is of course p, which will stay the same. Then there is this mu1, then there is this mu2, and then there is this covariance matrix sigma. So how can we estimate this is we will find out. The first estimate was for p hat, or the first estimate was for p, which we are denoting it as p hat, and this is nothing but the sample, I mean, all the y's that you get. So I varying from 1 to n, 1 by n. Then second is we want for mu hat, third is we want for mu2 hat, fourth is we want it for sigma. So for mu1 hat, for mu2 hat, and for sigma hat. So what is mu1 hat? Mu1 hat, since it's a mean for instead of for the data set which is coming from class 1, this is not going to be nothing but the sample mean of the data points which has label 1. Okay, that's the thing. So we are basically doing xi, but indicator function of all the data points which belong to the class 1, and that is going to be all the yi's which are 1, right? So I range from 1 to n divided by sum over indicator of y is equal to 1. Similarly, if we have to do it for mu2 hat, instead of y is equal to 1, I'm going to give y is equal to 0. That's the only difference. And the covariance matrix, if we find the ML estimate, this is going to be nothing but my sample variance. Just like what we have is sample mean, the estimate for mu1 and mu2. We have the sample variance as the ML estimate for sigma. So this turns out to be 1 upon n. We are going to have xi minus mu1. Um, hat. Now we can use mu hat. So xi minus mu hat of yi and xi minus mu hat of y transpose. Calculating from what? Actually, so this is nothing but the sample mean. This is nothing but the sample variance. And now all the process are so all the process stays the same afterward. I mean, whatever we have used for the knife base, the same will follow for Gaussian knife base.
Sigma is a covariance matrix, right?
Yeah, sigma is covariance matrix. Just give me 1 minute. Yeah. So okay. So just for so sigma is my covariance matrix now, and mu is the main, like mu1 and mu2 are the main for these two normal distributions, and all the process what we have done for the knife base, the same follows for the Gaussian knife base as well. So now, like if we have to look out for the decision boundary in case of knife base, then it still turns out to be the linear, assuming the same variance for um, both the classes. So even for the Gaussian knife base, in case the covariance matrices are same, if the sigma is same for both the classes, then my decision function turns out to be linear. But in case we assume a different covariance matrix for my sigma 1 and sigma 2, for class 1 and class 2, then in that case, my decision boundary is not going to be linear. Okay, that's the only difference here. Yes, tell me. Um, any of you had any doubt in Gaussian knife base? I mean, it's everything is same here. It just the only difference is about um, that my xi's now are taking the real values instead of binary.
So, ma'am, in the place of covariance matrix sigma, we cannot use normal distribution sigma square symbol.
No, no, you can use, but here, since we are talking in higher dimension, we have taken sigma, I mean the bigger sigma, as a covariance matrix. But you can, I mean, you can have something like normal with mean mu and variance sigma square. Not a problem.
No.
Like in general, to denote the bigger class, I mean, we have taken it to be capital sigma. Okay, I would like to stop it here and we'll start with the problem for decade. So let's move forward. Let me do this.
Oh, ma'am, you are not audible.
Yeah, I'm sharing my screen. Hold on. I'm audible now, right? Yes.
Yes.
Yeah. Yeah, we'll do some questions now. Okay. So the first question is, suppose you have a 5-class classification problem where the class label is 0, 1, 2, 3, 4, and each training example xi has binary features f1, f2, f3. The question is, how many parameters do we need to know to classify an example using naive-Bayes classifier? That's your first question. So again, like it is not a binary classification problem. Now you have 5 classes. Just keep that in mind. You can work on this problem for some time. Okay. I see 3 different answers in the chart. 11, 39, and 18. What do you think? Which one is should be the right answer? Okay. Mayank, can you tell me how did you get 11?
Ma'am, actually, I have given 18 for 5 labels. We will take only 4, and by giving 2 to the power 3, e, that will be 8, and minus 1, 7, and for both sides,
What
there will
is
be 40.
8, 9? What is 8 minus 1? No, no. I mean, why 8 minus 1?
Ma'am, 8 minus 1, because since by getting 7, the probability of, if we have a probability of first 7, then we can find the probability of last one, or that reason.
Mhm.
So for 7, for one side, both will be 14, and plus 4, 18.
Okay. Okay. All right. You have gotten 18. Then Kiran has gotten 39. Kaushik has gotten 39. Shamanta has gotten 39. Kaushik, can you tell me how did you get 39? How did you get 39?
Ma'am, basically in this we have six
Mm-hmm.
level, 6 levels, and we have to find for 3 features. So it will be some mistake, ma'am. I think it should be 6 multiplied by 3 plus 2, that is 20.
6. So why 6? Now, how many classes do you have? You don't have 6
Right.
classes. You have only 5 classes.
Yes, 5 multiplied by 3 plus 2.
Mm, okay. Kiran, what are you saying? You're saying number of parameters without, but nowhere it is mentioned that. Um, I mean, if we are saying the knife-based classifier, it means it follows the class conditional independence, right? There are two assumptions that we make. One is class conditional independence, right?
Yes, my friend.
Yeah. Yeah. So what should be the answer here? Let me put it here.
Ma'am, is 15 5 times because 5 classes and 3 features.
Okay, let's see. So, mm, 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 wait. Hold on, my screen got stuck here.
So in this one, ma'am, we'll have to consider class conditional independence only, right?
Yeah, if we are saying time-based classifier and we know it assumes a class conditional independence.
It should be, I think, 5D plus 1, right?
Yeah, let's see. So we have
16 should be the answer, probably.
so now we don't have, I mean, we have 5 classes. So you should have 1, 2, 3, 4, 5, right? So y1, y2, y3, y4, y5. And if we know any 4, the fifth one should be okay to us. So from here we need 4 of the parameters. Now for each of these 5 classes that we have, uh, we have exercise taking the features f1, f2, f3, right? So if we talk about, if we look at f1, I mean, how many possibilities do we have?
8.
So total is 8.
Yeah, so 8 into, yeah, correct.
Yeah. So
Yes.
total is 8 here. And how many are these?
5. 5 into 8, 40.
40. So 40 plus 4 is 44.
4 as in the.
4 coming from these.
First,
Mm.
how did you take 4? There are 5 Ys, the classes.
Okay, okay, sorry. 5, 5, 5, 5.
5, no? 5.
Yeah,
45.
5.
No, ma'am. First, when you
Okay, okay. No. Okay, okay. This is 8. So for each of these, we have two choices. For F1, we have two choices. For F2, we have two choices. For F3, we have two choices. Okay. So you have 8 of total from the first. And how many are
Correct.
these? You have to take 5 of these cases. So 8, 5, 8 times 5,
40.
which is 40. And then for the yi's, I have 4 parameters. So total of 44 parameters is what we need to estimate.
ma'am,
Why?
this 8
Why
into
have 5 labels, ma'am, right?
Sorry, you have
5 labels, right? No, why?
but if you know the
Okay. If we know any one probability of
any
anyone,
one,
then we need 4 only.
then you need only 4 because we
Okay,
can
okay.
add those 4
Okay,
and
got it.
subtract it from
40
the
plus.
total.
Excuse me, ma'am.
ma'am,
Yes,
sorry.
yes,
So
Shweta.
all the time it has to be one less, is it?
Because see, if you look at the two classification problem, what was the case? You had only two classes, so we said for one we can say it is p, and for other it is going to be 1 minus p. So similarly, if you have three classes, so for let's say I can say this, if this is p1, p2, p3, I know my p1 plus p2 plus p3 has to be 1, right? So if I know any two, I can find the other one, right? And that's why 2. Okay.
Okay, so it is actually 1 minus 5. I mean 5 minus 1 actually. That same
5
thing,
minus 1, yes.
5 minus 1. Okay.
Yeah.
Uh,
Shweta, you
Excuse
had
me,
some.
ma'am.
Yeah.
Yeah, ma'am. Here we are considering our features are independent, right?
Features are independent, yes.
Yeah. So if features are independent, so for let's consider if we have y is equal to 0 label. For that label, we each feature will contain two value, either 0 or 1, right? So
Hmm.
in that case, we will be having the 6 as a parameters, 6 parameters for three features, right?
Why
When y
6?
because y1 will take a 0 or 1, f1 will take 0 or 1, f2 will take 0 or 1, and
No, no,
f3
no,
similarly
no.
f3.
No, it
Think
will
of it
be
as
2 to the power 3.
think of
You
it
know,
as coin toss experiment, right? So you have eight
while the
choices for this, right? You can have either one, 1 1 1. You can have 1 1 0. You can have 1 0 1. You can have 1 0 0. Then
But this
another
case is
four.
for dependent parameter, right?
Madam, it is independence, right? So,
Independence.
Yeah,
so
this case is for dependent, right?
you are writing for dependent.
No,
Yeah.
no. What?
Ma'am,
Ma'am,
you are writing the combination for dependence.
What
ma'am,
is
how
it?
you got 8?
Each
Means
feature is taking the values independently, right? So out of two values, uh, one free variable and another one is dependent. So it would come around for each feature. It would take one value.
you are saying there are three choices for each.
Yes. That is for feature one, like she said, it can take the possible values would be 0 and 1.
Yeah,
But
that is
it would
true. That is true. I mean,
no,
if I write
that is
the one,
one, right? So among the two values, it can take only one. So one free variable, one dependent there.
No. Tell me again. What did you say? If feature one,
In
it can
each,
take any. It can take either 0 or 1.
yes, either
What
it
was
can
it?
take either 0 or 1. So here it is one free variable, one
What do you
dependent
mean?
variable in every feature.
What do you mean by that? I mean, see, these are occurrences of three features, right? They're occurring independently. I don't know whether my F1 is 0 or 1. I don't know whether my F2 is 0 or 1. I don't know whether my F3 is 0
Ma'am, I am
0 or 1.
talking about F1 only.
Yeah, so
Because
F1 can
F1
take
is,
either 0 or 1. F2 can take either 0 or 1. F3 can take either 0 or 1. Just like the coin toss experiment,
yes,
where
yes.
if you are tossing, let's say, any three coin, my first coin can either take head or tail. My second
Yeah. So
coin
Ma'am,
every
parameter.
feature can take only one value, right, ma'am?
It's
yeah,
PNC
it,
like.
it
Yeah,
can
it is the
take
If
probability,
there are
ma'am.
three features, means 3 into 1, it would become 3 only,
hmm,
ma'am.
no, why? See, I'm writing all the cases with to you, right? I am saying these are the cases you can get. So you will get 0, 0, 0. You will get 0, 0, 1. You will get 0, 1, 0. You will get 0, 0, 1. 0, 0, 1, 1, right?
But
We don't have to look
that
at the
cases will be
combination, right, ma'am? We don't have to look at the combination, right, among the features, because each feature is independent of another feature, right?
Correct.
So there are three classes. So each feature can take one value. So yeah, 3 into 1. So number of classes into the feature can, the possible value for feature. So it would come
Yeah.
3 only, right, ma'am?
No. I mean, you are saying if F1 is 1, if you're saying if the F1 is 1, then F2 cannot be 1. Is it what you're saying?
No. I'm not telling like that, because
Then what are you
it is
saying?
free. That is feature one is independent of feature two and feature three. Like the
Correct.
same. So
Okay.
so we don't need to consider the combination, right?
Why not?
If you consider the combination, then it would become dependent, right? So we are going with.
How is it making it dependent? This is independent, right? If F1 is independent of F2, F2 is independent of F3, given the classes.
Oh, ma'am, I think you are considering like the values to be the parameters, but like we have to consider the probabilities. No, each feature is
Oh.
associated with a probability, and that is independent of the
Yeah, that's what I'm telling.
probability of the
That's
other
what you're saying.
feature. Yeah, so
Okay.
there are three features. So
There are
three features together contribute to like three three parameters.
no, it will be 6
You're
parameters.
saying that.
yes, ma'am. So
Okay.
that's what same what I'm telling.
Okay.
Why
Sorry.
six?
Because we should not look for the combinations, right?
Sorry. Yeah, now I understood what you're saying.
Yeah,
Okay.
because it would go through dependent nature.
Uh,
Okay.
okay.
So each
I
feature can take only one value. So three
Uh,
classes. So 3 into 3, we have to multiply 1 with 3. So it would come around 3.
no, there will be two values. Each feature taking two value, either 0 or 1.
One is free
Yeah,
variable, one is dependent, right? Among that two feature.
No. If we are
Two
considering feature
possible
1,
values. Among that.
in the lecture, no, sir has taken the probability as a parameter, not the values.
No. I got it. What you're saying. What were you saying, Shweta? I was just listening. Can you
yeah,
repeat?
I was taking like if from start, okay, if we are considering y is equal to 0, okay, so we fix that thing, okay. Then again for f1 we will be having two values, either 0 or 1, means for parameter f1 we will be having two for feature f1 we will be having two parameter, when y1 is equal to 0 and f1 will take 0 value, and y is equal to 0 when f1 will take 1 value. So we have to consider two parameter. So
Yeah,
same
correct.
for three features we will be considering six parameter when value of label is 0. So we will be having as value 0, 1, 2, 3, 4, 5 value. So for each we will be getting 6 into 5. So that is 30. And for y we will be considering 4. So 34 will be the answer.
Yeah, I got. I think that is what even she was mentioning.
Yeah.
Yeah, no, yeah.
But I guess
Sorry.
he was saying only one parameter will be there. No, we will require 2 parameter for feature 1.
Okay. Let me restart this. I think I just got confused with something else. Let me restart. Yeah?
Ma'am, create graph, then it will be easy.
I will just do it. Okay, let's see. Okay, so we have P1, we have 4 by 2, 5 by 3, by 4, by 5. Okay, so we have Y1, Y2, Y3, Y4, Y5. Okay. And for here, this is 4 parameters. There should be no doubt. Now, for each of these, given each of these classes, I have 3 features now. So 3 features here, 3 features here, 3 features here, 3 features here, right? So how many so from here we need D, right? Which is 3. And 3 into how many? 5. 3 times 5, which is 15. Okay. And plus 4 from the top. This is 19.
But we have choices. These are binary, right, ma'am? So we can take two, na?
Ma'am, 0 and 1 also. Y1 has
0
0
and
and
1.
1, then
No. You have 3 features with you.
Right.
Okay. You have let me just write. So this is
Okay, got it.
P of
Understood.
1 for 1. P of 2 of 1 in class label 1. P of 3 of 1. Right? So there are 3, you have 3 features. So you have like 3 into 15 because there are 5 of such cases. So 3 times 5, which is 15. So 15 from here is what do we need. Now the total number of parameters that we will need is 19. Right? Is
But
okay?
ma'am, P1 0 and P2 0, P3 0 also will be considered.
yes, ma'am. P1 0, P2 0, P3.
Yes. I have written Y1, Y2, Y3, Y4, Y5. You can, that's why I have used all the superscript 1. Okay. But yeah, you got the idea, right? We need, it is going to be P1 0, P2 0, P3 0, P1 1, P2 1, P3 1, P1 2, P2 2, P3 2, right? You got it, right?
Ma'am, I
So,
think, so ma'am, given P1 1, like given Y1, if we know P1 1, so we can easily find out P1 0 also, right?
if what can we find? P1 0.
Given Y1,
Given
given
Y1.
Y1, given.
Sir,
Suppose we know
ma'am, it
P1
would
1.
be 6 for Y1, I think.
No, tell me first, what were you saying?
Just a
Given
second.
Y1.
Given Y1, and suppose we have the knowledge of P1 1.
P11.
So
Okay.
we can easily find P1 0 also then, right? It will be 1 minus, right?
But they are independent, no? P.
They're independent.
They are
Okay,
class
got it.
condition independence.
Class condition independence. Okay.
Yeah. So they all are independent of each other. Okay. So total of 19. So 19 is the right answer for this question. So whoever has given answer as 19 is correct. All right. Okay. Let's move to the next question.
I just have one small query. In this one, since you mentioned like we are considering P1 1, why are we not looking at P1 0 or P2 0 and P3 0?
Ma'am,
Yeah,
it would be
I just
34,
said
I think.
I just said you can do that. So I mean, since we have y to be 0, 1, 2, 3, 4,
Correct.
for
It should be
0,
30.
for 0, it is going to be P1 0, for P1 1, sorry, P2 0, and P3 0. If I
If
have
we
to
look
write,
at that way, it will be
it is
34, right,
P1
ma'am?
1. Why
Ma'am,
34? What is
we are
34?
talking about binary features 0 and 1.
Ah, so
That's why we are saying P1 1 and P1 0 also.
why?
Exactly.
What? That's why P1 1 and P1 0. What do you mean?
On the basis of binary features. Ma'am, you
So,
have written P1 1, मतलब Y1
P21 and
had,
P31.
on the basis of we are saying P1 0 also. Binary
sorry, can
feature for
someone
0
tell
and
me
1.
what is the? Is there anyone who understood what the issue is? Because this is correct. What we have just explained. Did anyone understand?
Ma'am, no, what we are saying is that, ma'am, since you have mentioned P11, P21, and P31, so
Hmm.
since these are binary features, so we'll also have P10, P20, and P30 as well.
Yes, we are multiplying it with number of classes, right?
Yeah, exactly.
So you will get all the features, right? 15.
Yeah, and 15 is the
Possible,
correct.
the features can take two possible values, 0 and 1,
Correct.
binary feature. So
Correct.
we have to stick with one value. One is the free value and another one is dependent value. So think like that. Okay, so 3 into five classes. We have five classes. So first one is k minus 1. K minus 1 is number of classes minus 1. First
Correct.
plus k into, okay, number of possible values that feature can take into dimension. That's a solution. So k, we are multiplying it with k. We are finding the possible value for one class and we multiply the result with number of classes and with dimension. Got it?
So just like, yeah, so just like, think of it as you had two classes. So if you had two classes, what did we do? So if we had just two classes, one parameter came from here, right? So y is equal to 0, y is equal to 1. And let's say if I have number of features to be, let's say t, so let's say think of it as d, number of features to be d, then how many parameters I need to estimate from here? D. How many parameters do I need to estimate from here? D. So how much
2D
it is?
plus 1.
2D plus 1. So similarly, it is here also as well, right? Since
Madam,
now you have three features, F1, F2, F3. So for every class, you are going to have three features. And how many are there? So three from here, three from there, here, two, three, three. So 3 into 5 is 15.
Each feature can take one value.
Yes.
Got it.
understand
Got it. Understood.
and
Okay.
in the feature the F1 F2 F3 the values are only binary. If it is having more values, but then also the answer remains 19, right? In the given problem, if we add more options instead of binary, if it is 0 1 2 3 4 5, then also the answer remains same, right?
No. Number of
No.
options minus one.
Yeah.
Mm. Number of options minus one. So one is the free, one is a dependent, all the others are free. Here
So
it is
now,
binary.
So,
So
so for example, if it is 0 1 and 2,
yeah,
that time we have to take their how
two
many.
values are free variable, free values, and one is dependent value. So you have to consider two.
Okay, so instead of 5 into 3, it will become 5 into what? 6.
no, that is fine. See, you're confusing. Here you're getting confused here. So see, if you're now taking y belongs to 0, 1, 2, but if I'm saying there's still each of my xi has their binary features, it means f1, f2, f3 if we have, they belongs to 0, 1. then what it looks like? It looks like, I mean, you have three classes, and for each of these
No,
classes,
no,
I have.
ma'am. I'm telling five classes, but the features are having more values. Meaning,
Hmm.
it is instead of 0, 1, let's say 0, 1, 2 for for the features.
Okay. Okay.
Then at that time, what will be the answer?
That time also it will be same.
That's what
If
I'm
the
asking.
naive assumptions are there, no, like class given feature independence. If that is assumed, then there is no difference. I mean, the
Okay.
number of parameters will be the same. If there is no such assumption, then number of parameters will change.
So in the given problem, if we just bring in one more value for the feature, the answer remains same because at any
No,
point of
no,
time it
no,
may
no.
come.
Answer won't be the same. Number of possible values minus one. There also you have to see the free variable, dependent, free values and dependent value. One will be the dependent value, right? So you three possible values a single feature can take, right?
Okay, fine. I think
That's what you are telling, right?
we can move forward, ma'am.
Yeah,
Don't
I
want
think
to.
this is. We can come back to this if all the questions are done. I think this is taking a lot of time.
Here we have put 2D, madam, because the possible values are 2. So that is why possible 2 minus 1, 1. So that is missing here. 2 into 1 into D actually.
Okay, okay, okay. Yeah, okay. All right, let's move to the next question. I will come back to this at the end. Okay. Um, so here the question says a Gaussian knife-based model is trained on a given data set. For an unseen data point x, the following two values are calculated, which is probability x given y is equal to 0 is zero point 0.4 and probability x given y is equal to zero point 0.6. Then what is going to be the predicted label for x? So any other answer for this question? I see Mayank has given option C. Okay. Yeah. So C is fine, right? Anyone, any of you has any doubt? I'm hoping no, because all of you are the right answer. Anyone has any doubt why the answer
But
is not C?
you can predict, right? You can give labels why it is not zero. I didn't understand. It should be either one or zero.
I mean that is okay. It can be either one or two, but um,
But we don't know probability of y.
we
So
don't know what
We know
probability.
probability of y is we don't know, na? Probability of the
Yeah.
labels we need.
So if you have to make prediction, what do you have to do? You need to do probability y is equal to 1. Given my x, and probability y is equal to 0. Given my x.
like, if the question says that the probability is mutually exclusive or independent, right? Then how this question changes?
What if the probabilities are mutually exclusive?
Uh,
What do you mean by that? But
X, if the occurrence of X
see, the
doesn't depend
question
on Y.
says
It's totally both are independent. Okay, for example,
module x.
I'll give you a real life example. Right?
Yeah, tell me.
So, irrespective of uh, you're going to buy a house, irrespective of uh, both husband and wife working, what
Hmm.
and whether you have a pet dog or not, the loan will excess your earning capacity. Whether pet dog is there or not in your house, that's independent. But whether loan will be approved or not, right?
Okay.
So you give see you give all the information to the loan model. Okay, I am giving all the information. I have a pet dog, but pet dog is not say why is your pet dog, right? For this model, it doesn't matter at all. Then how this question will be reframed?
How this question will be framed is you're
See,
asking.
because imagine X and Y is a model, right? See, for a naive base where use a model, you do whether the loan has to be approved or not. Say, for example,
So why?
probability of uh,
Go ahead.
yeah, I am replacing X and Y with the features. Okay, right? Can be replaced.
X and Y with the features. Y is not a feature. Y is a label. So here we
Say,
can
okay,
say
label. Okay, correct. Label. Okay.
loan is approved to be 1, loan not approved to be 0.
Yeah,
Maybe we can.
correct. Okay. Now I'm just now I'm going back. I'm feeding the model with the data, saying that okay, salary of both husband and wife, and then I have a pet dog or not. That's it. That feature is not at all required. So then, whether it will label whether that pet dog is there or not, or how it will work. I think. You understood my question, right?
It's okay. Let me rephrase if this is what you're trying to say. So you're saying yes, my Y is whether the loan is approved or not. That is my label,
Mhm.
and now you're adding some features, something like whether I have a pet dog or not, which
Mm.
is not even needed for
Correct. Mm.
this probability to work. I mean,
Mm.
the loan to be approved or not.
Mm.
So those are redundant features, and how does that affect the prediction? Is that what you're trying to say?
So what will be the predicted label if that is what you're saying? Okay, I got
Yeah,
it
but
now. Yeah, you're saying that the predicted label will be to approve or to disapprove, right? So we don't have sufficient information for this. Yeah, I got what you're saying. Thank you. Go ahead.
Okay. So here the only thing is we need to know what is the probability for y is equal to 1 or y is equal to 0. Then we can easily
Uh,
say that it is the prediction. But
in
in
this case,
our case, it's not
you
provided.
can say that like whether I am earning more than for a 1 crore house, whether I am earning more than 50 lakhs or
But those are
the,
features, and features,
uh,
the features value are already given to us.
okay,
Yeah. I mean, probability of x given y is equal to 0, probability of x given y is equal to 1, they're already given to us.
okay.
That is not a problem.
Then we should
What
be
we
able to predict, no?
basically, yeah,
Predict the
but
label.
but we don't know what is the probability of y is equal to 0 or y is equal to 1. And
Okay.
that is needed for us to solve here. That's why I was writing this. So this is going, I mean, if you have to predict it to be either y is equal to 1 or 0, I need to know what are these probabilities.
Okay.
And to
So
find out these,
if I give that there are for 1,000 x uneven instead of saying uneven data point, if I give that it's 1,000, what happens?
so it doesn't matter, no? Still my probability y is equal to 1 is missing. Doesn't matter how many x's or how many features you add. Still, I don't know what probability of y is equal to 1 is in this question, or what probability of y is equal to 0 is. Still, I cannot say for sure that this is the probability I'm going to get for this, or this is the
Okay.
probability I'm going to get for this. So it's not possible. I mean, don't think of it as a real life example. This small problem where you have to just know this is the simplest thing you are given to you. Can you calculate the probabilities or not? If not, if you can calculate, what are the information needed? And if you're not able to calculate, what are the things that is missing here? Doesn't matter how many features you add. Those probabilities are already given to you. For this,
So
if I
what do you
in
mean by uneven data point here? What does it mean? What is
where is
uneven?
uneven data point given here?
For an uneven data point x, what does that mean?
Where is it written?
No, here
It's
Gaussian
unseen,
naive.
unseen.
Unseen.
Unseen. Sorry, uneven, not unseen. Sorry.
For an unseen data point, for which is x.
Oh, okay. Okay, fine.
Okay.
Got it. Yeah.
Okay. All right. Let's do the third question. So the question says a binary classification dataset contains n examples belonging to 0, 1 to the power 3, such that the first feature values for on all n examples are 0. Assume that no Laplacian smoothing is done. Then what should be the value of p1 hat of 0? Is the question clear to you from the state, from whatever is given here? Is the question clear, or should I explain once?
Yes, ma'am.
Okay. You can proceed. I'll wait for some time. You can try it out.
No, if you apply all the features as 0, it should be 0 only is the answer. Right? All the features you are seeing for search and features. Answer is 0. I think.
Yeah, I see two of few of you have already answered it. It's zero answer only. That's correct.
No, usually what in practical how we work is you, for constructing a model, you divide it to whatever columns you have, which is an alphabetical column, you change it to a numerical column and then apply the labels actually 0 and 1.
Hmm. So okay, it's a binary classification problem, right? So you have either y is equal to 0 or y is equal to 1 again with us. Now, what we're saying is we have n examples. So we have, let's say, 1, 2, so on till n. And each of these n example, the binary classification dataset contains n examples belonging to 0, 1, the path 3. It means we have three features here with us. So we have feature 1, we have feature 2, and we have feature 3. And then I can write by here, which can take either 0 or 1. So what we're saying is the first feature values for all the n examples are 0. Okay. So the first feature is all 0. So assume no Laplacian smoothing is done. So what is the value of P1 hat of 0? Okay. So I am going to look at all the examples which has labeled to be 0 and like which are labeled like y to be 0, and the first feature value is uh, the first feature value is what we are going to look at. So but in this case the first feature value for all the examples that we have is given to be 0, right? So this will turn out to be nothing but answer to be 0.
Ma'am, is it asking that what will be the predictor for the feature 1? Is the question is asking that?
So it is asking something like we have 1, 2, 3. um so let's say this is P1 not art, right? So it is asking what is this, P1 not hat?
So that means the predictor for the first feature, is it like that? And
Hmm.
it is answer in the question itself. It is saying that P1 not position 1 is always 0, right?
Yeah,
And
in the question it is given that the first feature value, which is f1, for all the example it is 0. So if you have to find P1 hat of 0, what do we look at? We look at all the examples where your label is 0. So probability along with it that my feature 1 for all the example should be 1, right?
So it is asking something like a probability of F1 given y test is equal to 0. Uh, Probability that F1 is equal to 1 given y test is equal to 0.
Yeah, it is asking something like that what is the probability that given y is equal to 0, my feature f1 is 1. Sorry, my feature f1 is 1.
feature of F1 is 0, no?
That's why it's 0, no? That's why the probability is 0.
No, why ma'am is writing F1 is equal to 1? It is always 0, right?
No, no, it is asked here to find out, na? What will be
It's
the value of
P1 now.
P0
It
and
is 1.
10?
Since F1 will be always 0, it is given
F1 is
that
always 0, na?
probability of
In all
F1
the
will be
entries.
1 will be 0.
This means you have to find this, okay? But you can see that feature 1 always take the value 0. So this probability will always turn out to be 0.
Okay. So it is asking what is the probability of f1 being 1 when y is equal to 0 given.
Yeah.
Okay.
So it's more like among all the examples that you have, which are labeled as 0. So if you look at this, so among all the n examples that you have which are labeled as 0, so let's say these many are labeled as 0. What fraction of what fraction contains this feature f1? Okay, this is what it means by writing this. What fraction contains your feature f1? So here, none of these contains the feature f1. So that terms will be 0 divided by whatever number of examples that we have with label 0 or something. So that will always be 0, because there aren't any examples where my feature f1 is 1. Right? Feature f1 is always 0 for all the examples.
And ma'am, how does it differ if the Laplacian smoothing was applied?
So how does it differ if the Laplacian smoothing is applied? So what do we do in Laplacian smoothing? Can you tell me? You would have seen this in the lecture.
We'll have to add a case basically.
We'll add some pseudo examples.
Yes.
So in this, so what do we add? So we add maybe all the
One.
ones with label 0 and all the ones with label 1. So we'll add two pseudo examples. So maybe x1 pseudo is we can say, and x2 pseudo we can say. So now once we add this, now you can see there is at least one example which contains a feature f1. So now the probability, this estimate that we have, is no longer 0. It will be some non-zero value. So that probability, even though it's a small probability, but it is not 0. Right?
Okay.
So just because one of the feature is not occurring at all in my training, where that shouldn't affect the other features that is present. So that's why we want to make sure that the probabilities are not 0. It shouldn't give the value to be 0, and that's why we do the Laplacian smoothing. Okay, so that at least the features which are there, that um, should give us a reasonable answer. Okay, the answer is 0 for this question. Okay, question number 4. So again, we have a linear model trained on this data matrix X, which is of shape D cross N, with that is 3 cross 4, and the label vector Y. So P hat and P hat J yi are the estimates of probability Y is equal to 1, and P hat J yi is the estimate of probability of Y is equal to yi given if J is equal to 1. So you have to find what is the value of P hat 3 of 0 and what is the predicted label for the 0.100. This might take some time. I'll give you, I'll wait for some time. Okay. So, yeah, the answer for the first part is 0.5, and the answer for the second part is 1. So, Shanmugan, Ariba, your answers are correct. Mayank, your first options, first question. Yeah. Any doubt? I mean, this is nothing new. To whatever we have done in the first three question. Is anyone finding it difficult to calculate this?
Ma'am, can you give the solution for first one?
Okay. Okay. So you have to let's write it down first. So how many data matrix shape of B cross L? So we have feature 1, we have feature 2, we have feature 3, and then we have the labels. How many examples do we have? 4. So 1, 2, 3, 4. So feature 1 takes the value 1, 0, sorry, 1, 0, 0. The label is 1, 0, 1, 1. The label is 0, 0, 0, 1. The label is 1, and 0, 0, 0. The label is 0. Okay. So we need to find out p hat 3 of 0, right? So we need to look at the examples where the label is 0. So basically this and this. Now we are saying for the F3, um, so in F3, there is one with the feature, sorry, one with the F3 to be equal to 1, and there is one example where F3 is 0. So out of these, out of all the labels with, out of all the example with label 0, which is total of 2, how many has the feature F3 to be 1? And that is only 1. So the answer is 0.5.
Ma'am, where is it mentioned to find? Okay, FG equal to 1. Okay, okay.
Hmm? Is it okay? Mayank, is it clear?
Yes, ma'am.
Okay. What about the second part? Anyone finding it difficult for second, in solving the second question? Okay, if not, we can move forward. The
And the
answer for,
predicted label can we find directly from the table only?
no, not from the table, you have to solve, no?
Okay. Show the solution also.
Okay. So again, how do you find the prediction? It is, you need to check what is the probability
Right.
of y equal to 0 given my x, and what is the probability of y is equal to 0, sorry, y is equal to 1 given x. Okay. So let's say we want to find this first. And what it is going to be? Probability of x, which is 1, 0, 0, given y, given y is equal to 1, times probability of y is equal to 1 divided by probability of x. Okay. Now we know the estimate for probability of y is equal to 1, and that will be 0.5. Fine. So this is 0.5. We can ignore the denominator, because even if we are calculating probability of y is equal to 0 given x, this is going to be going to be same. So just ignore the denominator. We can just work around with numerator. So now if I have to calculate, it is going to be probability that f1 is equal to 0 given y is equal to 1 times probability that f2 is equal to 0. No, it is 1. No? F2 is equal to 0 given y is equal to 1 times probability f3 is equal to 0 given y is equal to 1 times 0.5. Okay. So now given y is equal to 1, which is this and this. Sorry, not this and this, 1 and 3. I need to see uh, how many has label 1. So that is just 1, right? So 1 by 2 from there. So 1 by 2. Now, how many has f2 to be 0? So f2 is 0 and here also f2 is 0. So this is 1. Okay? So 2 by 2, which is 1. Now, how many has f3 to be 0? So 1 has 0, another is 1. So it is 1 by 2 again, and into 1 by 2. Okay. This is going to be 1 by 8. Okay. This is fine. Now, can you find it for y is equal to
Yeah, got it.
given x? Yeah, you got it. The same process we can follow. Okay. All right, let's move to the next question. Okay, so this is also very similar. Okay, let's do this. But this is very similar to what we have just seen. Okay, I can go to the next question. Yeah, it's better. Well, let's do this. Question number 5, we can try it out. We'll share this slide. It's very similar to what we have done in the previous question. So here the question says you're working on a text classification problem using a knife-based classifier to determine whether an email is spam or not spam. You have trained your model using a dataset of 1000 emails, with 600 of them labeled as spam and 400 labeled as not spam. You have collected statistics on the occurrence of 2 words. So we have 2 words with us, which is one and money. And for the keyword 1, label of email to be spam, probability is given to this. And I mean, this is the information that is known to us. So now let's say if you receive a new email which has both the words one and money, okay, and you want to classify it using knife base. Okay, so use a knife base formula to calculate the probability that the new email is classified as spam. So you have to find out what is the probability that y test is spam. And remember, my x test has both the words one and money. Okay, so you need to find this probability. You need to find this probability. Okay. So I see two answers. Shanmugan, your answer is correct. Mayank, it's wrong actually. So okay. Let me discuss this question. The question says, what the question asks is, you have to find uh the probability of. So it says, use an IBS formula to calculate the probability that the new email is classified as spam. So what is the probability of y test is spam given my x test, right? So this is what we have to figure out. So probability of y test to be spam given my x test. Okay? And let's maybe for making it simple, maybe let's call spam to be 1 and non-spam to be 0. So spam to be 1 and non-spam to be 0. So what is x test? Since we are saying there are only two possible features, so my x test should look like f1, f2,
1 month.
right? So how can we calculate this? This is nothing but probability that my f1 is equal to, so new email contain both the word one and money, right? So it is basically probability of x test, which is f1 f2 transpose given y test is equal to 1, meaning spam, times probability of y test is equal to 1, okay, divided by probability of x test. Now what is the probability of y test is equal to 1? So if we look here, so how many
Point,
spam emails do you have?
0.6.
And 2. Sorry. This is no,
Point
not
6, no?
correct. 0.6,
Point
0.6.
6.
No, yeah, 0.6. So 0.6. So this is given to be 0.6. Now, what is the probability of, maybe we can call f1 to be 1 and f2 to be money. Okay. So f1 to be 1. So y test is equal to 1 times probability of f2 given y is equal to 1 times 0.6. Okay. So now look at this table. So spam we have in these two cases. So given y is equal to 1, what is the probability of f2? So that is, let's call f1 to be 1, the feature 1, and f2 to be money. Okay. Then it is 0.45 times 0.3. So 0.45 times 0.3 into 0.6. Okay. Now in the
How is it?
denominator,
0.45.
0.3 is given, 0.45 is given, and 0.3 is given. Right?
Okay.
So feature 2, let's call it money. Feature 1, let's call it 1. So those values are given to us.
Okay, since they have appeared together, that's why, right?
Yes, there are only two possible words, and we are saying the new email we have received, they have both the words, one and money. Okay. So 0.45 times 0.3 times 0.6. Now, what is the probability of x test? So it will be all this probability plus we will add also the case where y is equal to 0. So that would be 0.05 times 0.02. So 0.05 times 0.02 times 0.4. And whatever you get after solving this is your answer. And this turns out to be 0.995. Any doubts?
Can you just tell once the denominator part
Hmm.
is EX test?
Hmm. Yeah.
Denominator is
So
the
what is
probability.
probability of X test? Okay. This is probability that X is probability of X given Y is equal to 1 times probability of Y is equal to 1 plus basically law of probability. Probability X given Y is equal to 0 times probability Y is equal to 0 time that's all. This we have already found in the numerator. So all we need to know is this. And probability Y is equal to 0 is given to be 0.4. And what is this part going to be?
Got it.
This part is going to be probability of F1 given Y is equal to 0 times probability of F2 given Y is equal to 0. Right? So those are also given to us, which is 0.05 and 0.02. So this is 0.05 into 0.02 into 0.4. Okay? And you just add with this. It's fine. Any questions? Okay. See, there's one more question.
Ma'am, how many questions we did? 6 questions. No.
We did 6 questions, but we skipped one because both were similar. Two of them were similar.
Okay.
So we have one more problem. Okay. All right. So here you have 10 examples basically, and there are three features. One is color, one is type, another is origin. And the label is basically satisfied. If satisfied, label is yes. If non-satisfied, label is no. So we want to classify a new object with the property that color is red, type is formal, origin is domestic. So what what class should we predict this example to? Is the question. Again, this is not anything different. It's very similar to, I think, all the questions we have done.
So
I mean,
X test is basically red, formal, and origin on and domestic, right?
X test is red, formal, and origin. Red, formal, and domestic. So now you have to predict what is the label for this object. So label whether whether it is you are satisfied or not. That is the question. So try this out. Just wait for some time.
Ma'am, how do you get 6 after 9?
Oh, I think that is duplicate, is it? Wait, red casual imported. No, it's 10.
Typo.
Yeah. Okay, so two of you have answered it to be no, and actually that's correct. Um, so okay, let me just quickly go through this. So what is it that we have to find out? So this is my feature one, this is my feature two, and this is my feature three, and this is my label y. So I have to say what is the probability that y is equal to 1, y is equal to 1 given my x test. So given my x test, which is the color red, type formal, and origin domestic. Right? This is what we have to find out. So now what is this going to be? This probability that the feature f1 is red given y is equal to 1 times probability that feature f2 is formal given y is equal to 1, and probability that feature f3 is domestic given y is equal to 1 times probability of y is equal to 1. And what is that probability? So 1, 2, 3, 4, 5. So it is 0.5. And what is the probability that f1 is r? So out of all these, yes, I need to see how many has r. There is this 1, there is this 2, and there is this 3. So 3 by 5. How many f2 has f? So 1, 2, 2 by 5. How many f3s has d? So this is 1, 2, 2 by 5 times 1 by 10. Okay. So what do you get? You get 3 to 6, 12. 12 divided by 125 times 2, which is 250. Okay. Now, similarly, we have to look for probability of y is equal to 0 given this x test. So in that case, it is going to be if 1 is red, we have to see, right? This is 1 and 2. So 2 by 5 times, we need to look at formal. So that is going to be 1 and 2 and 3. 3 by 5. What is going to be domestic? So this is
3 by 5.
1, 3. 3 by 5 into 1 by 2. This is 6 out of 9, 18 divided by 250. So this probability is going to be higher for us. So the answer is going to be more. Okay. I hope it is clear to everyone. All right. So that's all we had for week 8 questions. Okay. All right. Anybody has any doubt? Okay.
Ma'am, you'll share this PDF by tomorrow.
Yeah, we'll share this PDF by tomorrow. Yes. Sure.
On the dashboard, right? Portal.
On the portal, yes.
Ma'am, can I ask some questions?
Tell me.
It's according to the theory. Actually, I haven't seen the week 8 lectures. I have seen first 2 lectures of professor. So in which
Okay.
he describes about a dice, and in the second case he describes about coins.
Mm-hmm.
So he took the example of a spam email.
Okay.
So what was the algorithm in the first case? That in the first case, he tossed a coin to see if it's a spam or not, and then in the second phase of first case, means if
He
it's a
tossed eight.
if it's a spam, okay. So then it goes to cube. So a
Hmm.
cube has d
8
faces.
face. Yeah.
8 faces. If yeah, 2 power 3 is 8 faces. Yeah. So
Hmm.
it has d faces, and
And now for the non-spam, you have a different die which also have 8 face.
it also have 8 faces, and
Yeah.
all the dimension depicts the length of the dictionary, means the capacity of the dictionary it has.
Hmm.
Yeah.
Yeah.
And in the second case, he took the example of coins only. Okay, so he tossed the coin. It's a spam or not, and then he arranged D coins, I think.
Yeah. D
That
coins. Yeah.
yeah. So can you explain how means? I only want to get to know how it different. If you
Okay.
can tell us, because
So, okay. See, in the first case, like when we like you want to generate a story which can help us in uh, deciding um so there are two generative stories I talk about, right? In the first case where we toss a coin, and now for the two, for if it's head, I'm going to look at that eight
spam or
face
not?
die,
Yeah.
eight face die, and if it's tail, I'm going to look at the another eight face die, right? So when we did this, okay, so we saw that the number of parameters that we need to know or that we need to model in this case is was going much higher, right? You
Yeah.
would have seen that the number of parameters we have to estimate is more, which
Mm-hmm.
was some which turned out to be
To power
2
D
to the power.
is
No, it
yeah.
was more than that, right?
Yeah,
It was
it's around 10,000, ma'am. 2 power 10,000.
why 10,000? So 2 to the power
Because
d.
yeah, D is the length of the dictionary, means the capacity of
It's the
dictionary.
end of dictionary, yes.
Yeah. So
So
means
2
I
to the
want to
power
ask
d.
that what is the difference between taking a cube, taking a dice, and taking coins? If you can explain
There
it
are
through
two
diagram.
different. So okay. So these are two different ways in which we are generating our
Mm.
examples. Okay. So in the first case where we are rolling a die,
Mm.
the eight face die, there if we are generating it using that way, then the number of parameters that I have to estimate is much higher. Okay. But when we are doing it using this coin, where we tossed a coin, we saw it was head and tail, and depending on the number of words in the dictionary, now we are tossing those many number of coins. And from there, we saw that the number of parameters that we had to estimate was 2d plus 1.
Two
But
D.
whereas in the die example, die case, die story, we had 2 to the power d something.
Yeah, 2
Okay,
power D plus
which is
1, I
quite big. Number of parameters that you have to estimate is quite big.
think.
So
Mm-hmm.
that will not be preferable, right? So we want the number of parameters to be lesser.
Yeah. I got this, but see,
Hmm.
in the dice case, why
Hmm.
we are getting 2 to the power D? Because let's take the particular case of that dice. It has D number of features, D number of
Mm-hmm.
data sets. Okay,
Uh-huh.
hello.
Yeah, yeah, I'm listening. Tell me.
Yeah, so any any feature can occur or not occur. Okay, so it
Hmm.
is 2 into 2 into 2 into it is D times. So it became 2 to power D. Okay,
Okay.
and in the second case, there is a coin. Okay, so what professor said, as far as I remember, that
Hmm.
each coin is has given probability, some
Hmm.
probability, and it's like
Some,
it will
yeah.
flip or not. Each coin will contain the words.
Huh, right.
Yeah, and it means and there is a probability that this word will flip or not. So here also there is flipping chance. There is a flipping chance of 1/2, na, means it will flip or not flip. So it's the same case. How it is D plus one something, and in the other case is 2 power D. That I want to know how.
Okay. See, in the first example, so what we had done, let's think of it as the email example itself. Okay. So there, sir has taken, let's say there are three words, and so three words in the dictionary, let's assume.
Okay.
Now, the very first thing is we toss a coin to see whether it's from a spam world or it's from a non-spam world.
Mhm.
Okay. So if it's from a spam world, the way we want to generate our example is we toss an 8-face die. Okay, we roll a 8-face
Yeah.
die. Okay. So when you have an 8-face die, so this is one die, okay. But then if you are in non-spam world, then again you have a different some another 8-face die which you will roll in case the example or yeah, example is coming from a non-spam world.
Huh.
Okay. So um so total number of possibilities, like if you have 8-face die, or the total number of possibilities that you have is 2 to the power, I mean 2 to the power 3, right? Because it's binary feature.
Ma'am, can you
Which is
explain the
binary.
diagram? Can you explain through the
Okay,
diagram?
diagram. Yeah. See. So you have probability P. Okay. And let's say Y is spam, and let's say Y is non-spam.
Can we drop him?
Yeah, if you can drop. Yeah. If you don't have anything, you can drop. Now, see. Here what they are saying is uh, uh, we have a 8-face die, right? So you have 3 features because we're talking about
Yeah.
3 words in the dictionary.
How?
W2, W3, right?
Yeah.
So this is going to be 2 to the power 3,
Hmm.
right?
3
So
permutations.
we'll roll a 2 to the power 3 face die. Okay. Now, even in the another case where it is non-spam, I am going to roll a 2 to the power 3 face die. Okay, it's some different die, but an 8-faced different die. Okay. Now, if you have to estimate the total number of parameters here, this is one. I mean, this is one parameter that you need to know,
Hmm. Yeah.
right? What about if I am looking at this case? How many parameters we need to know? We need to know 2 to the power 3 minus 1.
Hmm.
Hmm?
Yeah.
Is okay? And how many times does it occur? Twice. I mean, again, of course, it's for the non-spam case, but it's basically twice.
Hmm. Yeah.
The total number of parameters I needed was, in general, 2 to the power d minus 1 times 2 plus 1.
Hmm.
Okay. But in the second story that we had formed, there what we said is we roll, I mean, we toss a coin, which is the same. And if it's spam, which is let's say 1, and if it's non-spam, which is 0, I am, so let's say the number of words in the dictionary is D. So toss a, I will toss D number of coins. Okay.
Okay. Okay.
D number of coins. For
And each
both,
coin contains a word.
yeah, each coin will tell you whether this word has occurred or this word has not occurred.
Mm-hmm.
D is basically number of words in the dictionary.
Mm-hmm.
Okay. So for this, for y is equal to 1 case, you have d number of um, d number of parameters that you want to estimate.
Hmm.
Okay. And how many are those? Even on the non-spam side, you have
D.
same d number of features that you want to estimate. I
Huh?
mean, d number of parameters you want to estimate. So this is 2d plus 1. So, I mean, both are two different ways of generating this. But when we took this example of this die, rolling a die, the number of parameters we had to estimate was quite big. But in this case, it is less, which is just 2d plus 1.
Ma'am, but each point means for let's take y is equal to 1, then each coin can occur or not occur. Okay.
Yeah, I mean each
Let's
coin
say
will
how
either take 1 or 0.
money is there. Money is there. Okay.
Either
Money.
0 or 1.
Yeah, either is 0 or 1. So 1 means it will occur and 0 means it will not occur.
1 means that word has occurred.
Occurred.
So let's say you have some word in the dictionary and these are here. So if this word has occurred in the email, I will, if it's an email example, it's a 1. If it is not occurred, it is 0.
Mm-hmm.
Yeah.
Then each word has permutation of 2 means 2 into 2 to the power d na
2
like
into
2 into 2 into 2 means there are 2 to the power d permutations in that case.
So this is um
It can occur, it
for,
cannot occur, as we are doing in 3 there.
so see what we are doing is we are, for each of these words that you have in the dictionary, this is word 1, this is word 2, this is word 3, and so on. I am associating a probability to each of them. So
Okay.
for the word 1, there is a now a coin which you will toss, and based on that, you will have some probability. So
Okay.
let's say if it's coming from a spam word, which we are denoting in the superscript, what is the probability of the word 1 with label 1? Okay. For the second one, what is the probability of the word 2 with the label 1, and so on. Okay. So these are the probabilities that we are associating with each of the words that you have in the dictionary. So how many such I mean, this is going to be D, total of D, and this is also going to be total of D.
Total of d
D, right? Because there's going to be D, no? Because total number of words in the dictionary is D. They will have B D 1.
no, but in the previous case we also had d, so didn't we write d? I'm not able to get that, sorry, I'm asking.
In the previous case, we had rolled. So in this case, um, in this case, if it's from a spam world, we are rolling a die.
Okay.
Okay, we are rolling a 2 to the power 3 face die. Right? So you have, if you just look at cases of, this is just the cases of ones and zero, right? So 1 1 1 1 1 0 1 0 1 1 0 0 and another 4, right? Now if you know any 8 of it, sorry, any 7 of it, you can find the other one. So that's why it was getting to the power 3 minus 1.
Yeah, but that's what you're saying, that it's a permutation. So why we are not getting the permutation in the second case? Because what we are doing, what is probability is the total number of permutations. It's the total cases of permutation divided by